Welcome. Today we're going to talk about higher order derivatives. By that I mean derivatives of derivatives of derivatives and so forth. First I'll talk about the concept and notation. Then I'll give examples. And we'll talk about a specific kind of example of objects in motion. So, first we're going to talk about what it is. Well, if f of x is some function, I put dot dot dot, because I don't actually even care about the function right now. Its derivative is f prime. But notice, this is a function, but f prime is in itself a function, right? It's got an x in, and it's got a formula. So it has a derivative of itself. How about the derivative of the derivative? How would you notate that? Well, it's the derivative of the derivative. But that's awkward. So we want a better notation than that, especially if we take its derivative, because that gets really ugly. So, notice the prime of the prime? We have a nice notation. This is just f double prime. Or the second derivative. What is the second derivative? The second derivative is taking the derivative of the derivative. That's all it is. It might mean something, and actually in graphs it has a very specific meaning. It has to do with the kind of the concavity, the kind of how fast the graph curves. Because you think about it, what is the derivative? It's the slope at any point. So if the slope's positive, it's going up. If the slope is negative, it's going down, and so on. What is its derivative? It's how fast that slope is changing. So imagine I'm doing that and changing. I'm going up, and then I'm changing slopes. That's the sort of thing that you get from the second derivative. That's called concavity. We'll talk about that in another episode, but right now, what about the derivative of the derivative of the derivative? That would be the third derivative. How would you notate that? Hopefully, you can figure out. That's the third derivative. Now, this can go on. You could have a fourth derivative, or a fifth, or a sixth, and you could keep putting primes. But let me ask you a question. What is this as a derivative? Look at that. Even on the best of resolution, you're going to be hard-pressed to figure out how many primes I put there. Now, it's not common to need that many primes. I'll let you count it. Did you get it? There are actually 21 primes. So if you were looking at that, you'd either roll your eyes, you get an eye strain or something. We need a better notation to note that one. So what we do is, when we need it, we can just put parentheses there, and that's how many derivatives we are taking. So this could also be written as f parentheses 2, but that's not as efficient. This could be f parentheses 3, but still, that's not very useful. When you get around 5, it's probably useful. And again, this is not common. This doesn't happen very often. Let's try an example, not of that, but of higher order derivatives. Here's a function. I want to know what the second derivative is. So, try it out. Remember, we're taking the derivative of the derivative. Okay, well, in order to do that, we need to take the first derivative. So I'm going to erase this prime here, so I'm going to actually calculate the derivative. I'm going to get 1 plus x squared here, square. The top is derivative of the top times the bottom, minus derivative of the bottom times the top. So I get 1 minus x squared over 1 plus x squared quantity squared. I want the second derivative, which is the derivative of that. And that's kind of messy. So the top, well, it's the derivative of the quotient rule there. So we take the bottom, we square it. And the squared means to the fourth power. That part we can do. The top, it's the derivative of the top times the bottom minus the derivative of the bottom. Now, there are tricky rules to figure out what the derivative of the bottom is. And we don't have them. The chain rule specifically, it's not that tricky actually, now that I think about it. But I don't have that, so I'm going to actually, up here, figure out exactly what that is. Because the chain rule says if you've got a power outside, what can you do? But since we're not going to use that, I'm just going to multiply it out. And for this one, it'll work. Later on, if we had one more time, it might be too much of a headache. That's the function. So its derivative is going to be what? 4x plus 4x cubed. times the top. Now, remember when we learned the quotient rule, I said you should always multiply the top out? It's true, but I don't want to. This is just too messy. So I'm not gonna. If you want to, you can. Can things cancel? Probably, but let's worry about that also another time. This was just to show you second derivatives. And it should also tell you that if you start with something like this, the second derivative is pretty darn messy. The first wasn't so bad. The second one's much, much worse. Now here's another one. I'm not even going to take the second derivative. I'm going for the 11th derivative. See parentheses 11 of this function. And you think, I have to do it 11 times. So we start thinking, what can we do? Well, what happens when you take the derivative of x? What do you get? 1. It's constant. What if you take the derivative again? What do you get? If you take the derivative of 1, you're going to get 0. What about 2 or x squared? Take its derivative, you get 2x. Take the derivative again, you get 2. It's constant, so you get 0. How many times did it take? For x squared to go to 0, took x squared goes to 2x. Its derivative is 2. Its derivative is 0. So in 3 times x squared's derivative, so the third derivative of x squared is 0. The fourth root of x cubed is going to be 0. The fifth derivative of x to the fourth is 0, and so on, all the way up to the 11th derivative of x to the 10th is 0, and all of these will be 0 too. A little bit of reasoning saves us a lot of hassle, and this one actually is just 0. You should practice some of these before just going on and doing that. But I want to look at a specific kind of example. So, the example is position and motion. If we have an object in motion, if s of t is its position at any time, say it's in meters, and t is in seconds, we usually use v to represent the velocity. Velocity is the rate of change with respect to time. So what is the derivative of this with respect to time? It's going to be 3t squared minus 8t plus 0. And the units are going to be what? Well, velocity is something we actually know a little about intuitively because it's related to speed, although speed is always positive. Velocity is the same kind of idea. It's like miles per hour or whatever. The units here are going to be meters per second because those are the units I gave you. What about its derivative? Its derivative is acceleration. Acceleration is also something. Because of cars, we all kind of know what acceleration is. It's the change in velocity. It's the second derivative of position. So we're taking the derivative one more time. 6t minus 8. And maybe you know about the units of acceleration, but they're going to be that per second. So it's going to be meters per second squared. Now, Newtonian mechanics, when Newton came up with the laws of motion, that's as far as he went. But it turns out we need to go a little farther sometimes. And in the 1960s, when they developed the moon launch, they needed to look at the third derivative a lot. So rather than saying third derivative with respect to time of motion, which was awkward, they needed a word. They had velocity here, they had acceleration here, so they needed a word that represented sudden changes. So the word they came up with was jerk. Now, they didn't mean that as an obnoxious person, they meant that as a sudden motion. But if you ever don't like somebody, you can call them a third derivative. Of course, that probably won't help, because if they really are like that, then they'll think you're a nerd, and it won't help at all. But anyway, that's the third derivative of t. And it's the derivative of this. And its units are going to be meters per second cubed. You're not likely to see those except in some unusual differential equations involving friction or other velocity-based forces. But this is motion. It's related to multiple derivatives. And hopefully, with some practice, this will all make sense. Until next time.